Okay, let's see. So this one's going to be about derivative applications. We have two problems. These are a little bit longer, a little bit more involved, but this is really good stuff to know, especially if you are in high school taking AP Calculus. These problem types are found both on MCQ and FRQ actually. And also, if you're just in college taking Calculus 1, this is also very applicable because it's a little bit more, I don't want to say abstract, but it relies on more conceptual understanding than just concrete examples with computations in it. So let's talk about this first problem. So the graph of f and g is given. I don't know, it's a little bit unclear, but I'll draw it here. The black curve is what we mean by f, and then this lower curve, the blue curve, is what we're talking about as g. So we have two functions that are defined using f and g. We have p and q, where p is the product and q is the quotient between those two. So what we are being asked to find, and we're asked to find two different values. So the first one is, what is p prime of 2? And so the first step is, obviously, we're not going to jump right into evaluation. We just need to know what p prime of x in the first place is so that we know what we need to be calculating. So if p, and especially if this is an FRQ portion, you're going to want to show this work. This is, every part of a solution like this is very important to get all the points. So if p is equal to f times g, and then that means if we take the derivative of p, we need to do what rule? Well, it turns out we have a product, so we should probably do the product rule, which is going to be the left times the derivative of the right plus right times the derivative of the left, right? So we have left times the derivative of the right. And really, since we're just talking about the function notation, it's just going to be g prime. We can notate it that way. And then plus right times the derivative of the left, and that's going to be an f prime. So this is what we mean by the derivative. So now when we substitute that 2, we plug in the 2 and evaluate that, we're really looking at p prime 2 is equal to the function f. What is f at 2? We'll multiply that by what is g prime at 2? And we're going to talk about the relationship between derivative and slope. Those are, almost synonymous ideas. Is a rate of change is the derivative. Slope is change. And then now we have g, the function by itself, evaluated 2, and then multiplied with the change, so the slope of f, specifically at x equals 2. So what we're going to do is we're going to find these 4 individual pieces of information. Once we get that, we know that we can just come back to kind of our master equation, right? That's going to get us to the conclusion that we desire. So f of 2. That's going to be a little bit more straightforward to find, because identifying what a function equals at a certain point is pretty simple. Here's x equals 2. So if we just kind of follow that up to the black curve, because that's what f is, we see that that's just essentially going to be 7. Right? So f of 2 is 7. And likewise, we want to find the function value at g. So the function value of g at x equals 2. So once again, here's x equals 2. We come up to the blue curve. And notice that this isn't going to be explicitly on an integer value, right? So here's 3. And it looks like it's going to be 3.5. Now, with these kinds of problems, you can mostly assume that that's the case. If you don't want to assume, if you want to know that you know for 100% sure that this is actually not an approximation, that we're eyeballing it, that it's actually going to be 3.5, we can do that. We can do that with just remembering a little bit of algebra. So if we can get, notice that here's a point right here, and here's a point right here. And the slope of this little segment, right? So the rise over the run, well, it's -1 because we're dropping. And then we run over 2, right? So the slope here is -1 1/2, right? So we're dealing with negative 1/2 decrease right here. Well, so that how do we interpret that, right? That means for every single time that we go +1 in the x direction, we drop down 1/2 in the y. So if we're here at 4, and so at x equals 1, we're at 4, we're desire x equals 2. So once we get to x equals 2, we need to subtract 1/2 from 4, and that is 3.5. So it is, you can do it that way. So 3 plus 1/2, let's see, 3, 6, 7, I think it's 7 halves. So these are the two function values. And so now you might be wondering, okay, that's all great, but how are we supposed to figure out f prime and g prime at 2? Remember that conceptually, f prime, so the derivative of f is its slope. So when you see this, you should be able to go back and forth between graphical interpretation, just the theoretical, the analytical interpretation. F prime at this case is its slope. We're asking what is the slope of the function f, so what's the slope of that curve at specifically x equals 2, okay? And we've been looking at x equals 2 for a while. Up here now, because we're back to f, what's the slope of this line? What's the slope of f at x equals 2? We can see that's gonna line, it's gonna line up with this line segment here. We know how to take the slope of a line, right? Because the slope of a line is constant wherever that line is. So here we can do that rise over run idea. Here we can have these 2 points, this one and this one. Notice that for every single time we rise up 1, we go over 1. In other words, the slope is 1 divided by 1, or 1. And so the slope is 1 for all of these x values. And so since f prime of 2, since 2 happens to fall on this line segment where the slope is 1, we can see that the slope of f at 2 is going to just be the slope of this particular line segment, which is 1. So derivative is slope. That's a very important idea, especially when you have graphical interpretation of derivatives. And so now g prime of 2. Well, now that we understand that, we're essentially just asking, what's the slope of whatever line segment right here? This is g at 2. What's funny is we actually already talked about this slope in order to confirm the function value actually here, g of 2. So we already found that this particular line segment, so the slope at this particular x equals 2 is going to be constant because its slope is just minus 1/2 at that line segment. So we have all 4 values, and the rest is just plug and chug, and we have an answer. So p prime of 2, the f of 2 is 7, and the g prime of 2 is negative 1/2. G of 2 is 7 halves, and f prime of 2 is 1. So we really have negative 7 halves plus 7 halves, and that's all going to come down to 0. So all that work just to find that p prime of 2 is equal to 0. But it comes down to a nice and clean value. That is how we solve p prime of 2. So now what we're going to do, I'll clear some of the board. And since this is a video, what's nice about a video is that if you didn't get everything written down, there's a button called pause, and then you can pause it. And believe it or not, the video will pause and you can have time to write stuff down. I'm going to create a board. So if you didn't get it written down, just go back and pause the video. So next, what we want to find to practice is q prime of 1. So the strategy here is exactly the same. And I think you're going to find when you practice these problems, they're really all the same problem in terms of the solution, the strategy, the overall strategy, the generic strategy is going to be 1, just figure out what q prime even is in the first place, and then plug in the 1, see what we need to find, evaluate those things using the graph, move forward from there, and we're fine. Okay, so q prime of x. What is that? Well, it's defined for us here, the function at least, is defined as f over g. So that's a quotient, which means the derivative rule we should probably use for a quotient is the quotient rule. So if you remember, the quotient rule is low d high minus high d low over the square of what's below. It's a nice little poem. So low d high, and that d is the derivative, means derivative. So all we got to do is slap a prime on that guy. So low d high minus high d low, and g is below, over the square of what's below. Low d high minus high d low over the square of what's below. I'll be explicit what I mean by that square. So that's what we're squaring. So all we got to do is plug in 1 everywhere we see that. So we have a q prime of 1 is going to be g of 1 times f prime of 1 minus f of 1 times g prime of 1. All of that over whatever we get evaluate for g of 1, we square that. So perfect. We have, once again, just 4 things we need to find. G of 1, so the function values at 1, and then their slopes at x equals 1. So we can do that work down here once again. So we have just f of 1. Just make the observation from the graph. What does f equal when x is equal to 1? So here's now x is equal to 1. I'll put a tick mark here. So this is 1, right? Well, that's nice and easy. It's just lands right here on 6. So f of 1 equals 6. And then g of 1 is, here's 1. G of 1, look at that. It gives us a nice easy value. We don't have to do anything funny. It's just 4. And then now, once again, derivative means what? It means slope. So you should be thinking when, in terms of this graph, f prime of 1, we're just wanting the slope at 1, x equals 1. Notice that x equals 1 here for f. We're still on the same exact line segment as we were for that previous problem. So we have to do no new work. This slope is going to be the same still. We're still just rising over 1 and running over 1. So our slope is still 1 for this entire line segment. So if we were doing f prime of 0, that'd be the same thing too, because all of these points, at least from what we could see from negative x equals -2, all the way up until essentially 3, not including 3, but up until 3, it's just the slope is constant and it's equal to 1. So f prime of 1 is 1, and then g prime of 1. Once again, you'll see we're still on the same line segment as we were before. Previously, we were talking about x equals 2, and so we were here. But since this is a line, the slope is constant. It's going to be the same for all of these guys. So we're still, the rise over the run here for this line segment is still just this negative 1 over 2. So this does not change. And so now we just plug these values in and move on. So q prime of 1 equals g of 1. Let's plug that in. That was 4. F prime of 1 was just 1. F of 1 is just 6. And the g prime of 1 was just -1 half. And then we divide that. So what was g of 1? G of 1 was 4. We take that value and we square it. And so do some arithmetic. We get 4. Let's see, 6 divided by 2 is 3. Then negatives cancel. So we have +3 over 16, because 4 squared is 16. So we're going to have some nice little fraction here. 7/16 is going to be the answer to q prime of 1 for this particular situation. So these kinds of problems are straightforward, so long as you just know the rule, know your derivative rules, be flexible with not always having each function explicitly defined. It's important to be able to work with just the concept of a function without needing it to be explicitly defined for you to compute derivatives directly off of. Remember that derivatives are just slopes. It's a rate of change. It's how something is changing. And you can really use that not understanding to work with graphs, with tables, with all sorts of different ways that a derivative might come up in either a multiple choice style question or a free response style question. So now let's move on to this last example. This one's going to be also kind of a little bit of a longer one. Okay, had to cut away there for a second. We have a function f. So a lot of times we think a math problem is hard, and we blame the problem for being hard when we just are kind of too lazy to just read the problem. So if it wants you to find the derivative when n equals these different things, maybe let's just do exactly what the problem says. So let's start with when n equals 1, right? So if n equals 1, that means wherever we see an n, maybe we should stick a 1, right? I hope it seems to be fairly straightforward to people. Okay, so f of x, x to the n equals 1. Oh my goodness. Sine x. Okay, so we want to find the derivative of f when n equals 1. That's great. We just have this product. And so I'll re-represent this. So it's just really x sine x. What's the derivative of this? So f prime, this is just a product rule. And you really got to get fluent with this product rule. If you haven't memorized it, just memorize it, because it takes 30 seconds to memorize and it'll make everything so much easier. It's just the left, whatever the left function is, times the derivative of the right, and then add the right times the derivative of the left. Pretty simple. There's a little fun mnemonic. It's just left d right plus right d left. Okay, so from now on in this video, I'm kind of just assume that you're going to have that memorized, that you're going to write it down, that you can know what's going on with the product rule, because it's very time consuming to explain it every single time. So product rule, left, derivative of the right, derivative of sine is cosine. And then plus right, which is sine, times the derivative of x. Well, that's just 1. So I'm not going to write down times 1 because it's not going to do anything. So here we go. This is the first answer that they want, is the derivative when n equals 1. Okay. So next, n equals 2. So believe it or not, we should substitute a 2 wherever we see the n, right? So when n equals 2, we should substitute 2 wherever we see an n. So x to the n equals 2. So x squared sine x. Beautiful. Once again, we just got to take a product rule. And it's going to be a very similar process. This is a lot of the, oh, I got to put the pen there. You'll see this is kind of gets a little bit monotonous, right? It's math is pattern oriented, and you're going to see that. So left times the derivative of the right. So derivative sine is cosine plus right, which is sine. Okay, now I have something a little bit more interesting, because the derivative of the left is no longer just 1, it's 2x. So we have something there. So we can say we have x squared cosine x plus 2x sine x. And there we go. So this right here would be your answer for when n equals 2. And once again, I'm kind of just going to erase this work and keep going, because you are watching this on a computer or tablet or whatnot on the internet, so you can press pause if you really want to write stuff down. So now, believe it or not, if we want to evaluate the derivative of f when n equals 3, maybe we should take n equals 3 and then plug that in, right? A lot of people, I'm trying to point out that a lot of these problems that seem unconventional or creative or unnecessarily confusing, they're not unnecessarily confusing. You just have to read it and then do it. So now we have x, n equals 3 now. So shocker, we'd stick a 3 where that n was. X cubed sine x. And the pattern continues. So now if we take the derivative, product rule again, x cubed cosine x plus sine x. Now this time we have 3x squared as that derivative of the left there. But really this is all just easy going, shooting turkeys, menial task of work. So there you go. We have one more. And actually, what I'm not going to do is I'm going to let you do this one on your own. So pause the video, and then I'm just going to write the solution. So give it a try. It's very, very easy. Pause the video now. And the answer you can imagine, f prime of x, assuming that the n is now a 4, is going to be x to the 4th cosine x plus 4x cubed sine x. So there's that. Very wonderful. And now you might be wondering, what if we didn't have to do this for every single derivative, right? What if we just took the derivative, but let n be any arbitrary number? So now we're saying n, it could be any constant value we want. We don't care what that is, right? So let's do that real quick. F of x equals x to the n sine x. So n is a constant. So when we do this problem, just treat it like an arbitrary constant. Don't overthink it, okay? All the rules still apply. So when we do f prime of x, it's just the left times the derivative of the right plus right times the derivative of the left. So when you do this product rule, think about the n as a constant. What's kind of for the process? We take the constant, we drop it down in front, and then we subtract 1 from the constant, whatever that used to be, right? So x to n minus 1. So really, we just did this in terms of n being arbitrary. So x to the n cosine x plus nx to the n minus 1 sine, pardon my little boo-boo there. We got an x still, right? Sine x. So this is what we would call the general formula of the first derivative of f for any value of n. So notice that you can try this. Plug in n equals 1, and you'll get the same exact result. Plug in n equals 2, you get the same result. You can plug in n equals 4,000, and you would get the right result, right? So a lot of times we often represent derivatives in terms of some, constants or whatnot, which can be powerful. So do these math problems conceptually, understand that you don't need an explicit example in order to do math and that the rules still work. So hopefully this was helpful in that regard. And that's going to be all for this video.